the screen I'm using for my presentation. So I hope my screen is visible to all of you. Not visible. Entire screen. Yeah. Is it visible to all of you? Yes. Can you see my screen? It's not visible to me, so I think it is not visible to you also. Not visible, right? Dr. Geeta, it's not visible. Even the screen sharing is not going to happen.
Stop sharing and again kindly share once more. Please click on stop sharing.
Okay. But there is no stop sharing.
It will be there, ma'am. Yes, once.
Let me just check it again. Still it is not there. Okay. If it is not there, then can you see my screen now? I'm going to take it to a different system so that I can put it from there. I don't know what has happened today with this.
Not going to rejoin. Ask everyone to rejoin. फिर कट करेंगे. Yes, ma'am. Screen is visible, ma'am. Screen is visible. Please speak something. Your screen is visible. Yes, ma'am. Okay, okay. Kindly speak, ma'am. We'll check. Participants का in the chat. Because until now that you will reach will close everything and okay. Ask the participant. I will inform you. Ma'am, okay. Yes, can we end the event and start the event? We'll ask the participants to rejoin again in a minute. Can we do that now? I will announce here. Okay. Yes, you can put it in the chat and then ask them to join in 1 minute now. We will start the event. Okay. Dear participants, we are facing some technical issue. I request all of you to kindly rejoin. We are going to end the event and then we will be starting the teams again. Kindly cooperate. Kindly join after some time, like 1 or 2 minutes. Thank you.
Hello, can you hear me?
Yes, ma'am. Your
Hello.
screen is visible and you are audible. Thank you.
Thank you so much. So still on my laptop, my mic is not on and neither camera nor mic are on. So I'm using a different device to for the audio and different device for the presentation. Yeah. So basically today we are going to discuss advanced devices. Please stop me if somewhere it is not audible. Please stop me. So basically today we are going to discuss the advanced devices. So it will be useful for the researchers, for UGPG candidates, for physics people, master or maybe PhD people and faculty members, so that they can find out that what is their job and how the students can be encouraged to do the fruitful work so that it can be published and it can be useful for the research community. So basically, there was the Moore's law. What was the Moore? Moore's law. Moore was actually the founder of Intel company, which is a very big player in the market. So today the biggest player is Nvidia. This Nvidia is biggest player because of some reason. Before this, the biggest player was Intel. I will feel a little bit difficult because there is another system and I cannot use the stylus on the screen. So I am writing with the help of cursor. So after maybe 2015, NVIDIA came into front because it brought GPUs, graphical processing unit, which is especially useful for the high-end computation, and especially this is for the gaming devices, gaming laptops, gaming systems and all these things. This was very helpful and very useful. That was because of specifically for high-end computations. GPU is supporting us. So Intel was not having the development of GPU or similar units. That's what it actually came in the background, and Nvidia came on the top. So today the semiconductors having the biggest market cap is owned by Nvidia worldwide. Nvidia is owning the biggest market cap, and Intel is on second. Google is also entering with the help of TPUs. Tensor processing units are actually similar to your GPUs. It is also for the fast computation. TPUs are by Google. So these are the big company players who are working on these semiconductors, and others like Apple, Amazon. All these are having their electronic business. So in that business, they are doing the fabrication and related activities also. So of course, those are also hiring the VLSI engineers, right? So there was some Moore's law. What was Moore's law? Moore's law was saying that every 18 months you will be having 18 months you'll be having your transistor size is just doubled on the single chip. Single chip means let us it's a 1 centimeter square. So on this 1 centimeter square, approximately your gate length is half and the transistor size is just double. LG, that's the gate length. In previous days, it was known as gate length was roughly known as the technology node. Technology node. For example, let's talk about 260 nanometer technology, maybe 560 nanometer technology, 180 nanometer technology. So all these are the technology nodes, right? So it was said that Moore's law governs, and approximately in 1.5 year or 18 months the transistor number of transistors will get double in a same area of the system, a same area of the device. So now what happened, we have reached already to 180 nanometers to, yeah, where we have reached here. We reached from some micrometers to nanometers, and in that nanometers we have reached to 130 nanometer, 90 nanometer technology node, 65, 45 and beyond. So when we have reached over here, the thickness of the here is approximately hundreds of micrometer. 100 to 200 micrometer is the air thickness. So it means if I have already reached to 130 nanometer, 90 nanometer, 65 nanometers, it means it is 1,000th part of my hair thickness. I have already reached to that. If we talk about the atomic distance between two silicon atoms, it is somewhere in some angstrom. This is a silicon atom and this is also a silicon atom. When this is not a single atom and a semiconductor material is prepared of this is approximately 5 angstrom. 5 angstrom means 0.5 in nanometers. So the distance becomes 0.5 nanometers. So if we are talking about, let's say 100 nanometer, let's say 100 nanometer I am talking about. So 100 divided by 0.5 means 200 silicon atoms only I'll be having over there. 200 silicon atoms for 100 nanometer. I am taking just 100 nanometer cross, let's say 0.5. If you will be taking it 1 nanometer, then 200 cross, a total 400 silicon atoms will be available. If I am talking about, let's say, single doping in this, a single atom is doped in this. Okay, so a single atom out of 200 and the total, let's say in 1 centimeter square, you are having 10 raised to power 22. Approximately 10 raised to power 22. So these two zeros will cancelled away and here you will be having 20. So it means 0.5 into 10 raised to power 22 is my doping concentration if I am having one donor or acceptor ion. And that is very heavy doping. That's very heavy doping. This much of doping means you are making P plus N plus and N plus region. There is no option for the intrinsic or let's say the lightly doped or those type of things. So it means the scope is getting reduced. The scope is getting reduced. So this is actually bringing us to investigate for the new devices, new physics, new devices and new dimensions. So that's what the Murray law is now no more into existence because there have been good enough scaling because of the Moore's law and we have already reached to some line. We cannot go beyond that particular line. Okay, so from MOSFET we will be switching towards FinFET. FinFET is what? FinFET is basically advanced version of MOSFET only. When you are reaching to the next level devices, it is coming into the picture. It governs the law by MOSFET only, but that at the same time it is going to give you the flexibility of Moore's law. For further scaling, it is going to give you the flexibility. Tunnel FET, TFET, it is abbreviated as tunnel FET is again FET, field effect transistor. So instead of MOS structure, of course it has the MOS structure, but along with that it has the tunneling phenomena instead of drift phenomena. High electron mobility transistors, negative capacitance FETs, junctionless FETs, gate all around. These are the topics which I am going to discuss today and how we will get benefited out of it. So basically, for a semiconductor person, you should know the things about material science, solid state physics, semiconductor processing, how the economics is going to play for the semiconductors, how the devices prepared out of semiconductor, how the transistors can be prepared, and then how the circuits can be prepared to the higher level, and then from the information theory and the control theory. So this way, this I have highlighted with the red line, this is the electrical engineering, right? This is the electrical engineering. But yes, this electrical engineering is deciding the semiconductor physics is the root of electrical engineering. It is the root. You are going to start with the semiconductor and then the device physics. After that, you will be developing the circuits. After that, those circuits will be utilized in your information processing, communication, control theory, all these things. So this is the Moore's law and more. Moore's law and more. This slide have been taken by from the ITRS. Nowadays it is IRD, International Roadmap for Semiconductors, right? how to delete. Okay, rubber is there, rubber is not there. Anyways, so look at this. This is the scaling more. This is the scaling phenomenon. It means we are reaching towards the more devices, which are no more MOSFET, but similar to MOSFET, but a little bit advanced version, so that the scaling can continue. So when you are reaching to 45 nanometer downside and more than 22 nanometers like that, 10 nanometers like that, you will be working with the FinFET. FinFET, you'll be working with FinFET. Okay, then another thing is the applications, and we now this is much more to be scaled down. And look on the x-axis, functional diversification more than more. So it means for analog RF applications, passive applications, HV applications, sensor and actuation systems, biochips, biocompatible electronics, and all these things, you need more than more. So for more than more, you need actually the systems which are having non-digital content and system in package. System in package is kind of your system on chip only, that is actually used in the digital context. So information processing is going to happen, and that is used in the digital context. So more than more are multiple devices which are especially working for these few applications, where your analog and digital domains are working all together, and that is packaged in a single system. So that is actually your analog and mixed signal IC design counterpart. So in this diagram, you can actually visualize that we are reaching from some 10 micrometers to some 1 nanometer. Let me tell you, right now 1 nanometer and 2 nanometer are in production. Soon these will be 1 nanometer and 2 nanometer, 3 nanometer, these will be commercialized soon. Few of the companies are targeting for these lowest technology node devices. So here you can see beyond CMOS, you have nanotubes, nanowires, quantum, and spintronics. These are the beyond CMOS devices. There are more than more devices where you have MEMS, NEMS, biochips, flexible electronics, which are combining the performance plus the natural sensing system all together. And this was the more than more. In more you were having multiple devices like FinFET, tunnel FET, gallium this can be junctionless FET, underlap, overlap FETs, etc., etc. So now let us understand what was the MOSFET and how the investigation towards the the advanced devices, advanced semiconductor devices can take place. So if you remember, this was a substrate. This was a substrate, okay, body, and on this was actually your SiO2 layer. On the SiO2 layer, this was your metallic gate. So this was basically MOS structure. This was MOS structure. This was extended. This was extended in this way, right? It was extended like this. Now what is going to happen? Look at this. This was your N plus. Drain was N plus. This is also your N plus. And the body is P type. Just below the gate oxide, the channel is being formed. The channel is being formed just below the gate device. Yeah, so just over here, the channel is formed, and rest of the portion, like this portion, is unused. This is not contributing to the current, carrying the current. But so what is going to happen is, this particular region is working like this is your P plus region and this is your N plus region. This was your N plus region, and yeah, some body over here. So this is your N region, N region over here connected with the P region, and then N region over here. So this becomes NPN transistor, and that contributes to leakage. So the drain is equivalent to the collector, and is the collector. If there is a small leakage in the body bias, then that contributes to the beta times of IB is the IC current. If you remember, if you can recall, beta times of IB, there is current amplification, right? So IC current, the collector current is contributed in this way. So it means the leakage is detrimentally harmful. It is not really good. Okay. In fact, this is I'm just showing one transistor, but there will be like Darlington pair of transistors will be there. That is made up of this N plus region, then the P region, and the channel is again N region, channel region, and this region, both all of these are connected. So there is a back-to-back connection and much more leakage is seen for the MOSFET device, and this leakage actually we need to stop. So in order to stop that leakage, we will be going to some other system, but let us deal with how we can go for how we can go from maybe 100 nanometers to 2 nanometers. So as I told you earlier, 100 nanometers means it is 1,000th of your hair thickness. 1,000 of your hair thickness, right? 1,000 times of your hair thickness. Hair thickness is 100 micrometers, right? 100 micrometers, 200 micrometers. These are the range for the hair thickness. So it means already we have reached over here. So the gate control, this is the length of the gate, right? So this gate control is actually loosened down. And if this is loosened down, we are left with the drain and source. So it becomes a semiconductor bar connected with some, if I'm not having the gate control, this control is not over there. Let's say it's been here, from here to here. So we have lost this control. Just now we have discussed this with the help of how in a particular 100 nanometers gate length, 0.5 100 divided by 0.5, that is 200 silicon atoms will be observed, and those 200 silicon atoms means only one impurity will be there. That impurity is already like heavily doped, so it is not contributing much, and in that case, yes, I'm sorry. So now this control, if it is lost, then it means it is no more working like your MOSFET device. So what we can do, we can make the channel region in this way. We can make the channel region in this way. So instead of this horizontal channel, we have made it vertical, and we will be applying the gate oxide all the sides, and the metal deposition is also going to happen all the sides. And if it is so, it means your gate is controlling this channel from three sides. What are those three sides? This is gate 1, gate 2, and top can be the gate 3, right? So in this way, there are three sides, and your gate is controlling all these from all three sides, right? So in this way, your gate control, even this was actually the smaller length, but still your gate control is more. So below 22 nanometers and all, you will be having FinFETs. Those FinFETs will be having the structure, the channel will be actually formed in this way. This is a fin type of structure, so we call this as FinFET. This particular thing is the fin, FIN. Fin type of structure, and because of that we will be calling, actually it is shown rectangular shape. You can do the simulations for the rectangular shape, but at the same time you are not able to prepare the exact rectangular shape. So it is good if you are going to take this fin in this way, and that was the actual fin. Fin means the outer the front part of a fish. The face is somewhat like this. I'm not able to draw it properly. So it means this portion, if I can replace it with this, that's what fin is. So this will be having this shape. That will be easy to prepare, easy to fabricate, easy to deposit the oxide, easy to deposit the metal instead of the complete vertical. Complete vertical will be a little bit difficult to prepare on. So many of the researchers will be using only two gates, one this and another one this. The reason is when we are going to deposit on this slanted line and this slanted line, let's say I am going to deposit in this way. I want to grow my oxide layer. So this growing the oxide layer, because there is some angle, right? So this is directly coming from the top, and on this it is directly coming from the top, right? So basically I will be depositing here a little less as compared to this portion. So because of that reason, people will be using the gate 1 and gate 2 left side and right hand side. This is your gate 1 and this is your gate 2. And this is not used as a gate because thin oxide is used, so that is not having the impact of this metallic layer into this particular channel, and that is not contributing much also. So for because these sidelines are occupying much more area, these sidelines are occupying much more area as compared to this. So because of that reason also people are not using this gate 3, because it is not contributing to the current flow, electric current profile of your FinFET device anymore. That's the reason. Okay. So now I told you earlier that there is some issue with MOSFET. This was the simple MOSFET. It was made up of, let's talk about N channels. So this was made up of N. This was also made up of N. This was made up of P. And this is the channel formation. Here is the channel formation. So look at this. This is there. This is there. This is one transistor formation. Likewise, with the help of this, with the help of this, and with the help of this, another transistor is formed. These both of these transistors are connected back to back. And this back to back connected transistor, actually, if you will look at the current, so current it means the base current, again this is getting amplified, and then the leakage through the channel is going to happen. So it means multifold leakage in the simple substrate. At the same time, you have to think about that this substrate is working like a sink for the heat also. If some current is going to flow, then I square into RT is the heat dissipation, where I is the current flow through this channel and R is the resistance offered by that channel and T is the time taken. So I square RT was the heat dissipation. If you are having this type of substrate, then the heat dissipation scene is really good and your device is working fine. So next to that, because the leakage was also a big problem. So in order to stop this leakage, there was a concept, okay, let's try with silicon dioxide on the top of the silicon substrate. So basically silicon dioxide is an insulator. It is an insulator. So it means the leakage from this to this is not going to happen. Okay, so it is not multifold current. So if the channel is formed over here, these particular regions are depleted regions, right? So a little less leakage is going to happen, very less leakage is going to happen. So this came into picture earlier. First of all, this came into picture, the conventional MOSFET. After that, this is known as the partially depleted SY. SY means silicon on insulator. S is this silicon on this insulator. This is the insulator. Silicon dioxide is the insulator. So because of that reason, it is called as silicon on insulator. It is taken for a larger gate lengths, where this particular active region is kept to be good enough, large enough, more than your active oxide layer of your gate. So for that, we will be using the partially depleted SOI MOSFET structure. The third one, you can see over here, the third one is actually, this is your N plus region, source and drain. Source and drain. You can see your oxide layer is just near to your the doped region. It is going to touch this N plus doping and this channel region. Okay, it is directly touching over there. So it means when the system is going to be active, large number of electrons are there just beneath this interface layer. So this portion will get depleted. This portion is completely getting depleted. So it means there is no leakage through this. There is no leakage through this because you have put the oxide, fix the oxide just beneath your doping. Means in this left side diagram, you can say that you have put it somewhere here, your oxide is somewhere here. So it means there is no chance that you can make it, there is no chance that you can make much more leakage. So the problem we faced was the leakage problem, and this leakage problem is removed with the help of this fully depleted SOI, and that is going to work at very low nanometer technology node. So that's correct. Now there is another problem. If I am talking about I square RT, so now my I square RT will actually, this is the heat and this is being dissipated in this particular region. And this heat dissipated actually is combining with the same region because the heat sink capability of silicon dioxide is very less. Silicon dioxide is working like the insulator for the electricity and for the heat also. It is not transmitting the heat. For example, it is somewhat like that we have rubber. Rubber is not able to transmit the heat, right? But if we talk about metals, metals are ready to transmit the heat. So every conductor is not able to transmit the heat, and every insulator is not actually is going to block the heat. So that is the material property. So just in the first slide, I told you that the material physics is also very much important for the electrical engineer. This is the material science, how the materials are going to behave. So the silicon oxide over here is not dissipating the heat much more. If it is not dissipating the heat, then what you have to do, you have to think about the different structure. You have to apply your engineering so that, see, we came to this because it was having the leakage issue, right? It was having the leakage issue. So first we came to this. Now these leakage issues were still persisting, so we came to this. Now we cannot go back and invite the same problem, whose solution we actually found that this is the solution. We cannot go back and invite the same problem. We cannot be on the same page. 10 years back, whatever problem was faced, we cannot go back and use that. So what we have to do, we have to apply some much more innovations for this so that much less heat can be dissipated. We have to investigate good enough insulators, or maybe the gate work function engineering you have to apply so that the less amount of heat dissipation can be there with the less amount of leakage. So this is a little bit a view that how the partially depleted, fully depleted, and the thin. So in fully there are two types. One is ultra thin and nano thin. So ultra thin SOI and then nano thin SOI layers are there. So here you can see what is the gate length. So for the gate length, you have 130 nanometers to the 70 nanometers for partially depleted. For fully depleted, typically it is lesser than 100 nanometers to 50 nanometers. And for nano SOI layer, you will be having the gate length 70 to 20 nanometers. Along with, you can look at the TSI. TSI is the silicon thickness. So the silicon thickness, you can see in partially depleted, it is much more, 100 to 100 times. In fully depleted, it is lesser than 50 nanometers, and in the thin, very thin depleted, it is 5 to 10 nanometers. So this is the advanced technology node. Nowadays it is going to work. This one is going to work nowadays. Yes, so in this example, the FinFET can be prepared. See, we moved from the conventional device MOSFET and we discussed what are the issues faced by MOSFET. So various issues faced by MOSFET. Typically, the very first issue we have discussed was, today we have discussed was the leakage current. Okay, there is much more leakage. And this leakage current leads to the sub-threshold issue. So the sub-threshold is 60 millivolt per decade. 60 millivolt sub-threshold leakage, sub-threshold swing, that is 60 millivolt per decade. 60 millivolt per decade actually comes from the point that there is a multiplier 2.5 times into VT. VT is at room temperature, the threshold, thermal voltage. So thermal voltage VT is given by KT by Q, that is nothing but 25.8 millivolt at room temperature 300 degree Kelvin. So if you will multiply this with 2.5, which you will be getting from the drift and diffusion equation in the off state, so you will be getting the numbers around 60 millivolt per decade. That's the number we are getting it from there. Okay, so if we are growing the FinFET in the conventional bulk or the just like your planar MOSFET, so the structure will look like this. This is the structure. So in this structure also, see the channel is this. So the channel will be facing similar problems in this also. That NPN, and because of that much more leakage in the substrate, that is dissipating, the power dissipation is going to happen through that, and that is not wanted, that is not utilized in my actual application. So the next one is the buried oxide silicon substrate. So in this case, whatever benefits of fully depleted channel will be having, those benefits are actually taken in this SY FinFET structures, silicon on insulator fully depleted. This is fully depleted because wherever the channel is, the doping of source and drain is finished, there we have started the buried oxide. So the buried oxide will look like this, and this white color is nothing but your gate metal, and just below this you have your oxide. Here you will be having your gate oxide. Okay, so from this you will be having this structure which is useful for you. Now what you have to do, if you are applying some physics model or something, you have to take into consideration this model. Okay, because the below you are assuming that there is no current flow through this. So there are models, physics based models are actually started with Poisson's equation, then we will be putting the boundary conditions. Those boundary conditions, then it becomes a mathematical problem. So it depends on your geometry, how is your geometry, whether you are working with 2D or 3D. If you can approximate that in 2D, that is really good. And then with the help of separation of variables method, because Poisson's equation is a second order differential equation, and if you are talking about 3D, it means it is multivariable equation, multivariable second order differential equation. So if you are not able to complete that with the help of separation of variables, then you have to take into consideration something else. For example, some approximations. So those you can get it from your simulated results, right? So simulated results will be taken from maybe Visual TCAD, maybe Silvaco, or maybe some other software you will be using, the device software you have to use. So this particular diagram shows what is the need of FinFET. This gives you the single gate. This is the single gate, means MOSFET, and double gate means it is FinFET. So over here you can see the DIBL. DIBL millivolt per volt, means 1 volt if you are going to apply at your drain, how much barrier lowering is seen in the channel region. So initially your MOSFET energy band diagrams were like this for a simple MOSFET. This is your drain side, this is your gate side. Channel, I have taken the horizontal cut, right? Now with the help of this, if I am going to increase my drain voltage only, I am not touching my gate, then also if the gate is very small, you will see that it will go in this way. So it means this was your barrier. This barrier, instead of having the good control of gate, it is having the control of drain also. That is not wanted, because it is, if the gate control is lost, then it is not your MOSFET device, no more your MOSFET device, which was having gate as a control. So this is what DIBL. This is the phenomena called DIBL, drain induced barrier lowering. Barrier means this height, energy barrier. So this is lowered down. So we call this as drain induced, because of the drain, the barrier lowering was induced. So yeah, valence band also will be seen similar to this. So yes, it was induced, the barrier was lowered down, and because of this, we'll be calling that this is your drain induced barrier lowering, and this is not good. So if you look at this diagram, look at for single gate and double gate. For single gate, you can see your DIBL is having very good effect. That is not really needed. If you look at the sub-threshold swing, so for single gate, it was actually much more. But for double gate, if you look at this, your DIBL is getting reduced. It is getting reduced. So this is for this, the arrows are going to present that these are the curves which are belonging to left hand side, and these are the curves belonging to right hand side. Okay. So from this particular diagram, we can visualize that the double gate is having lesser DIBL, which is represented by this blue color. Okay, and likewise the subthreshold swing, which is responsible for the power dissipation, especially the static power dissipation. See, in BJT and MOSFET, the key parameter in MOSFET was, in BJT the leakage current is more, right? In MOSFET, the leakage current was considered to be approximately zero when we were talking about the higher technology nodes, maybe 260 nanometers or maybe 560 nanometers, like that we were talking about. The static current was actually neglected as compared to the dynamic current, and because of that we actually preferred the MOSFET as compared to BJT. This MOSFET replaced all the BJT circuits. But nowadays, when we are talking about very dense circuits and all, this static power dissipation, if it is going to increase, it is going to create the problem. So this 60 millivolt per decade, if we can reduce it down, so it means my leakage current is less. My leakage current is less, it means, so from this diagram, I can tell, so basically, this is your drain current, right? This is your drain current. And if you talk about the gate current, gate voltage and the IV characteristics on the log scale and linear scale. So this is your ID and this is your VGS. So these are known as transfer characteristics. From these transfer characteristics, we will be having this subthreshold slope, right? From these transfer characteristics, we are going to have this subthreshold slope. Ideally, it is expected to work like this. But for MOSFET, it is somewhat like this. So it means much more current is going to flow. Let's say this is your threshold voltage and you are here. So it means good amount of current is flowing. You cannot stop it. But in this particular case, your VTH is here and you are here. So it means very less amount of current was flowing. So it means the static current, which is very less in case of lower subthreshold swing, right? But for MOSFET, it is limited, right? It is 60 millivolt or beyond volt. So you can see for FinFET it is coming to the 60 millivolt. When you are reducing the channel length, it is actually going higher side. Fine. So that gives you the reason why you should go for FinFET. Okay. So what can be the other things? In order to figure out what can be the other things with the help of which we can take it just like your research, further research in FinFET or let's say in MOSFET. So in this particular case, this work was done by one of my PhD scholar, Dr. Rashi Chaudhary. So she is at IIT Delhi now, pursuing her postdoc. So in this, two metal gates were taken up. Two metal gates were taken up with differing their work function. Differing the work function will create the some unwanted behavior, filtering out of the some unwanted behavior. For example, as I told you earlier, this is the end reason, this is the end reason, right? So if this is at the higher potential as compared to this becomes a drain, and this is the source. So if it is reversed because of some reason, then the source and drain are also reversed. But we want that it should not going that way. So basically, we are going to make this drain side region a little less effective, but the current is coming in the similar fashion. So because of that reason, the other metal gate is taken up, and these are the simulated results we have created with the help of this. So the results were created for the SMG, single metal gate and double metal gate. If single metal gate was there, both of these results were for fin. So single metal gate, you can see this dotted line, single metal gate was having lower value of your on current. While the double, you can see there is a good thing over here and the current is much more higher as compared to this. So simulation, TCAD simulations are helping us to visualize what would be the effect of some particular parameter change in your device and all, and then later on that can be fabricated if your results are really good and these can be fabricated, you can go further. So we should work all these kind of things on our T only with different parametric variations. So visualizing different potential and electric field profiles as it was taught, get better design software, better design systems. Yeah. So I'll take one more minute and then we will have a break for 5 minutes because we started a little late. So can we have a break of 5 minutes, or if you permit me, we can continue till 12:20 because we started a little late, right? Yes, type in the chat box if we can continue or we should have a 5 minutes break because anyway you started is from 11. And because of technical issue, the session started a little late. 11:20 it was started. So I just need 15 minutes more. Please type in the chat box if you can hear me. Dr. Geeta, can you hear me?
Yes, ma'am.
Okay, okay. So there is no response from the candidate. So let me take it further. So fine. Basically, these are the profiles. These are the contours. Yes, we should continue. Okay, fine, good. Thanks, Ankita. So this is the potential profile and this is the electric field profile. What we are going to do is we are going to visualize inside the wanted field. In the field, we are going to check how the electric field is going to be distributed. And this electric field distributed actually is responsible for the current conduction. How much the electric field, how the electric field is actually distributed, that is shown on the right hand side, these diagrams. and this is the electric potential. Electric potential and electric field, these are correlated with E is equal to minus dV by dx. So this is the electric potential profile. Differentiation of that is going to give you the electric field profile. So there are two gate 1 and gate 2, gate materials are there. Depending on these two gate materials, you can see the electric field at the source junction. You can see the electric field at the source junction is seen very high. In this particular case, where only one metal is there, the electric field at the drain is very high. And here also you can see at the corners, the electric field is going to be very high. While in this particular case, this electric field is much lower as compared to this one. And this is equally distributed among the channel. So what will be the impact of this? Since this electric field is, we have lowered it down, look at the red, this red is 4.4 into 10 raised to the power 5 kV upon kV per centimeter. Okay, so it means this is high electric, very high, and this blue is towards zero side, means minimal possible. So it means we have to bring it down. Why we are going to bring it down? See, more the electric field, it means the electrons are actually bombarding at very high speed. So yes, of course, good amount of current is going to flow, that is good. But at the same time, it is going to create the temperature effect. The temperature effect in the device is created, and that is going to create the problem for health of your device. Because if temperature is going to increase, our MOSFET also creates the problem with the temperature. Our static power dissipation increases multifold. Because if you remember, your sub-threshold swing is proportional to temperature. So even the internal device temperature is going to increase. This is going to alpha times of T, proportional. Your sub-threshold swing is going to increase, and that is working. Yes. So these are the few simulated results for the similar devices which I have taken from my PhD scholar's thesis. These devices are simulated for single metal gate and double metal gate. You can see in the first one, these are the transfer characteristics on the log scale. So this here you can visualize it in a good way, because the idealistic switching was going to happen in this way, right? But here the threshold voltage is seen later, and you can see this is approximately, this is the threshold voltage, and you can see over here the DMG is having the sub-threshold slope, which is like this, while this is having the sub-threshold string in this way. So a little difference is seen in both of these, but at the same time the off current of the single metal gate is decreased. It means the current is, the static current is more, and for this double gate it is lesser. Double gate it is going to be lesser. Double material gate, double metal gate, it is going to be lesser. Likewise, the conduction band energy band diagrams are shown over here. So if the conduction band is shown, the valence band, if you want to draw, you can draw in the similar fashion. You just need to draw 1.1 electron volt away from this, and that's the way how energy, the complete energy band diagrams can be drawn. So here it can be visualized that the single material gate is shown by red, which is offering the higher barrier, while the double material gate is offering the lower barrier. So the electrons are ready to move from this side to that side. Likewise, the electric field for both of these is shown, as we have concluded from the contours that the electric field at the drain side is very high for the single material gate, while for the double material gate it is lower down. that is good for the health of the device. Likewise, the electron velocity can be visualized. So you can see over here the electron velocity is slower down when we are moving towards the gate in case of double material gate FinFET. So it means this health related to temperature, right? So related to temperature, we are going to decrease it. So yeah, so for TCAD simulation, first of all, we will prepare our device. How to proceed? First of all, we will take some paper, previously reported paper. We'll take all parameters of our device. For example, here we have taken these parameters. Okay. Now we will be taking, we will be recreating the results, and we will be recreating those results, and we will be trying to figure out that we are getting the same results whatever the experimental data is going to propose, the same results we are having. And after that we will start the variations in our devices, maybe the metallic variation or the doping variation or something else. So that's the standard procedure, and we call this procedure as TCAD simulation. So many of the researchers, they start the simulation just like that with some example file or something, or some XYZ they will be presenting. But unless until you are going to do the calibration, your results are not valid, and your results will be rejected when you are going to publish somewhere. So first of all, do the calibration. So it is equivalent to that. Let's say I bought a wristwatch today from the market, and it is going to tell, currently it is going to tell that okay, it is 3 p.m. in the evening, but the time is 12 p.m., right? 12 noon, right? So it means what I have to do, first of all, I have to match my clock with the reference clock, and then I can believe on this. So likewise, your simulator works. First of all, you have to map your software, TCAD software, with the previously reported experimental data. That is nothing but the reference point. So after that, whatever variations you will be doing, those you can observe, and you can believe that your results are correct, and then that is publishable. So these are the different structures. I am skipping those portions, and let us come to the tunnel FET. So this is the tunnel FET device I have taken to introduce you the new advanced devices. So in this tunnel FET device, you can see that one side of it is P plus type instead of N plus. In your MOSFET, you had, see, it is double gate structure we have taken. This is also the gate, this is also the gate. So this double gate has taken from the FinFET structure. So if look at that, here on the top of that we used to have this metallic gate and this SiO2 covering this portion, and the bottom side there was the buried oxide, right? This way it was the buried oxide, right? So this was BOX, silicon dioxide. We call this as buried oxide. Okay. So in this particular, what we are going to do, we have removed that, as I told you, that our statics are, all our things will be lying in this for the device characteristics. So the upper portion, the gate oxide and metallic portion, that is being removed, and the lower portion is also being removed. The reason behind this is, that this is of our interest. So in case of FinFET, it was made up of N plus type source and N plus type drain. If I am going to replace this N plus with P plus, this gives me the tunnel FET. Why it is tunnel FET? Let us understand it with the help of energy band diagram. So I just need to concentrate on this. This is the channel portion just below my gate. That's the channel region. So when you are going to draw the IV characteristics, this was P plus type. So P plus type, and this is degenerately P plus type. So instead of P plus, let us make it P plus plus type. Generally, it is taken as, for silicon, it is taken as 10 raised to power 20 atoms per centimeter cube, and this portion is taken as 5 into 10 raised to power 18 atoms per centimeter cube. While the channel, which is considered to be the intrinsic, that is taken as 10 raised to power 15 atoms per centimeter cube p-type impurity. That can be boron, aluminium, or something else related to that. So this 10 raised to power 20 makes you your that particular region degenerately doped. As I told you earlier, as in case of Zener diode, degenerately doped means some of the valence band states are empty. You can see, and the Fermi level is inside your valence band. And in the static conditions, let me draw the energy band diagram. You will having the energy this way, that it is this is your p type. So yeah, draw this straight line. Now this is your valence band of this. For this you will be having, since it was intrinsic, so valence band is somewhere here. This was n type, so your conduction band is here, right? So the valence band is a little bit away from it. Now you are going to join all these. So valence band is actually added with this. Conduction band is of this 1.1 above from this, and this was what your p-type source region. So look at this. This is what your energy band diagram. So as I told you earlier, in case of Zener tunneling phenomena, this is having the filled states. This is the valence band EV. The lower portion is EV. This one is EF. And this one is EC, the conduction band. Okay. And here this EF is having the filled states. So these filled states, if because of electric fields an electron is even existing, that electron is not able to cross this particular barrier. This is the barrier width and this is the barrier height. Both of these are large enough, it is not able to cross that barrier. So what we are going to do is, look at this. This is the off state, which is this black color is similar to that. The off state, it will look like this. And in the on state, you are having some gate voltage being applied. So applying some gate voltage, it means this you are going to bring it down. Positive voltage means energy band diagrams are moving shifted towards downside. So look at this. This is being at downside. So this is at zero drain bias. So if I am increasing my drain bias more, what it is going to happen? I am representing it in this way. It is going in this way and then in this way. So in this particular case, you can see that this is your barrier width. This width has been reduced very much. It will come to 1 nanometer to 3 nanometers width. And the electrons are having good enough energy to cross this barrier and come to the drain with the help of drift phenomena, right? So this is known as bend to bend tunneling phenomena. Okay, BT. We call this as bend to bend tunneling phenomena, and it is in literature it is represented by BT tunneling phenomena. Okay, so bend to bend because it is going to tunnel from valence band to the conduction band. That's what we call this as bend to bend tunneling phenomena, right? So any questions so far? Let me quickly take one more minute to tell you about HAMT. And I will take just 5 more minutes to finish it off so that it can be really very helpful how you can take your research forward. And in the evening 3 p.m. we will be having the session on these devices as sensors from scientists from CD Pilani. So please attend that session. That is going to be very useful for you. So HAMT devices are, it is similar to your MOSFET, but it is not having your oxide layer between the metal and semiconductor. The oxide layer is not existing. Instead of oxide layer, you are having, there is some metallic gate, and after that direct Schottky junction is there, and that Schottky junction you will be creating. There are materials available in the literature which are changing their phase. So here you can see there is metal, metal is there. After that, this is aluminum gallium arsenide, and then after that again aluminum gallium arsenide is there, and the bulk is gallium arsenide. So at the interface of both of these, electron gas is being created. What is this electron gas? You can see at the interface of aluminum gallium arsenide and gallium arsenide, because of the dissimilarity in the band, this is going to take this shape. So this shape says that, look at this EF. This EF is already at this interface, this EF is already inside your conduction band. This is above your conduction band. It means these many electrons, these many states are already available over here. So this is just at this interface, one layer is, atomic layer is created, and that layer is full of electrons. Look at this, EF is already in the conduction band, so it means full of electrons. So this layer works like your conduction band. Okay, we call this as 2D EG, electron gas. EG is two-dimensional electron gas, and it is prepared in this manner. This 2D EG actually is the interface which has been created because of the lattice mismatch. Okay, and this is responsible for the current conduction. So different materials for this are used, like gallium arsenide, gallium nitride, indium phosphide. What are the applications? Precision sensors, next generation wired and wireless communication, power electronics especially, these can handle much more power, and advanced radars also. These are the few of the applications. Now I will take 2 more minutes to explain what is the junctionless and gate all around. So in the junctionless, what we are going to do is, I told you if I can change the work function. See, this is the MOSFET, right? So it is the oxide, and here I am making my gate work function. So if you remember, my gate work function was having 5GC, 5 gate and 5 channel, and there was some other expression over here, twice of 5 BQX, COX, like that. So this was the threshold voltage. Okay, so this is what 5G minus 5C. 5C is the work function of your metallic gate. If I am going to increase this or decrease this, so it means my VTH is going to, the threshold voltage of my device is going to increase or decrease, right? So threshold voltage of the device is increasing. Let's say initially it is, the threshold voltage of the device is 0.4 volt. Now I have increased it by some value. Let's say I have increased by 0.4. So 0.4 is being added over here, and the VTH becomes 0.8. It means at zero potential, what you will be having, much more depletion is seen over here at 0 voltage. So likewise, if I am going to make my 5G minus 0.4, it means at 0 potential, there are good number of electrons available over here. Good number of electrons means I have made the channel N type, right? So with the help of this, what you can do, you can modulate your channel. Just near the interface, you need to modulate. So modulating your channel with the help of, so let me take it in this way only. Let's take a double gate. So in this double gate, this is your oxide layer, and this is your gate. Gate 1 and gate 2, both of these are tied together. And this is your source terminal, and this is your drain terminal. So here this is taken off one type of N plus and N plus region, and here also it is N plus region. This is complete N plus region, and then the oxide layer is grown. After that, this metallic layer is grown in such a way that your work function is able to help in the zero bias condition. It is able to attract the holes just below the surface of this oxide semiconductor interface. So if holes are available, so I will be considering that this is P type, and that's what the junctionless concept is there. Okay, that's what the junctionless concept is there. In negative capacitance FET, what you are going to do is, you are going to make one more ferroelectric layer over here. Just above your simple oxide, a ferroelectric layer is placed, and this ferroelectric layer is going to give you the negative capacitance, and that's called as negative capacitance FET. Gate all around, what is gate all around? Let's say you have a cylindrical shape, a pan or something like that. That type of structure you can take it, and all sides of it just prepare your gate oxide, and on the top of it you can prepare your metallic layer. So now this is your N plus maybe drain, this is your N plus source, and this is nothing but your gate, and this is what the gate all around the structure is. So now I have completed from my side. If you have any questions so far, please feel free to ask. You may type in the chat box. I am really very sorry I have taken half an hour more. This is because of the technical issue we have faced. So let us stop for this session. Dr. Geeta, please stop for the session.
Yes, ma'am.
Stop recording for the session. Yeah, stop recording for the session. Dear audience, please let me know if you have any question. Please let me know. Otherwise, let us start at 3 p.m. So do you have any questions? Please type the question in the chat box.